Hi. Ow, that's loud. Hello, I'm David Maynor. I'm from Georgia Tech. I just lost my PowerPoint presentation, had to run outside and grab another copy of it. If you think skydiving's fun, you should try losing your presentation right before a speech to see what adrenaline feels like. So it's that time, I suppose. Sure you guys don't want to go see another speech? Something better, cooler, faster? Nope. Yeah, I'm stuck. How many people here are from corporate America? You know, not universities. Okay, how many people are from like educational institutions? How many are from the government? I paid my taxes this year. We'll begin in a second, I suppose. If I seem a bit lost, it's because this is my first presentation from a large group of people. Well, this isn't a particularly large group. It's larger than I've ever spoken in front of before. My first black hat. So if I'm doing something wrong, let me know. I have no problems with being corrected. Yep, I suppose that's about it. We should begin. Like I said, my name is David Maynor. I'm from the Georgia Institute of Technology, where we don't believe in firewalls. We don't really have that many on campus, especially at the border, which is a big problem because we seem to get port scanned and attacked a lot. Now, I know you're surprised, being the university, people want to hack us, but it happens. We, in lieu of firewalls, we try to build a very good IDS infrastructure, starting at the border, which was kind of hard at first, but we eventually got it working. And the biggest problem we found is that on dual OC12s, we were aggregating the data to a single point. On the dual OC12s, we seem to have a lot of false positives, which was a really large problem for us. Is my volume okay? All right. Which was a very large problem for us. We were getting 10 or so million alerts a day, and for a small 3-person group, that's kind of hard to parse. And even with some built-in, even with us building some of our own tools, modified greps and whatnot, looking for things that seem interesting, we still had a big problem because the amount of data was just so overwhelming. That's what led me to the idea for the talk today, a practical event correlation system for security tools. There's lots of vendors that do this, but being an educational institute, we don't have tons and tons of money to spend on them. So we could either do without or write our own. So we opted for write our own path. Basically, what I'm going to talk about today is how you can build your own. It's surprisingly simple if you don't want to go too complex. The biggest problem I was trying to address while doing this was the information overload, as I mentioned before. We just spent entirely too much time chasing a single host that was doing multiple port scans, as opposed to missing the one lone intruder. Did you have a question? Anyway? Oh, okay. Instead of chasing the one lone intruder that was actually compromising machines, the false positives were just outrageous. Being a large campus with 2.5 Class Bs, we could not accurately look through the data. We would. Everybody is familiar with IDS technology, correct? Well, we would see IDS alerts going to machines. And I'm sure everybody's experienced this. MSSQL worms going to Linux machines, and it gets alerted to be a critical machine, a critical alert. So we have to spend time mitigating that, only to nmap-o it and find out that it was only a Linux machine, and they don't run MSSQL. And the reverse was true. We would see a lot of the slapper worms, the SSL chunking encoding problem, attacking Windows machines, and we know they don't run anything secure. So we were trying to cut down on that to see past basically what the big problems were and get to the individual hosts that were actually doing things we deemed were bad. As I said before, we had we'd have large amounts of data we had to go through. And this would mean that we couldn't really respond to attacks in real time. For instance, if somebody was doing a SSH CRC32 exploit against a Solaris machine that was right, against a Linux machine that was a database server, we couldn't see it and do anything in time to stop it. The best we could hope for was an audit trail so we could later on go back and try to mitigate what happened, which isn't really acceptable to a lot of security practices. Although blocking it in real time would require basically cutting down on the false positives. Why write it yourself is a good question. There's lots of vendors that do this. I mean, there's lots of vendors that do this, and I'm not advocating that you don't use their product or that you don't spend any money on it. I'm just simply wanting to show you how easy it is to implement an 80-20 solution. You know, you can cut 80% of the solution for a significant return on investment, and then use something else for the other 20%. There's lots of vendors that do this, like Open, ArcSight, GuardedNet, eSecurity, NetForensics, Cisco, ISS, Symantec, Micromuse, and Network Intelligence. Some of these people are here, and they have good solutions, and I'm not suggesting that there's anything wrong with them. Just some people don't have the money to buy them, but you still need the technology. Things to keep in mind when you write or buy a product like this are things they do for you. One of the big things you want with security event correlation is normalization of data. Basically, what security event correlation is you have a lot of different security tools that generate a lot of data, which is different than 10 years ago when security individuals didn't have enough data to efficiently understand what was going on in their network. Now you've got everything from TCP dump, which can be used as an effective security tool, to multi-million-dollar security solutions from vendors. And they all have one thing in common, is they generate a lot of data. Checkpoint firewalls, PIX firewalls, IP tables even, Nessus, Nmap, all these tools you'll use will generate a lot of data. Now, some of this data is you can't use. I mean, it's throwaway data. For instance, in my solution, I don't really deal with filtered ports that well from an Nmap scan, so all that stuff's discarded. The biggest thing is that you make all these tools work together in an efficient way that will allow you to use information efficiently. Sorry, I'm a little bit nervous. The biggest thing you want is normalization of data. You have all these security tools, for instance, an intrusion detection system, a port scanner, a vulnerability scanner, a passive fingerprint detection tool, and perhaps a host-based or a network-based firewall. You want all the information to work together, or give you basically one view of it. Now, in order to do this, you generally have to either write something that takes the output of the tool, like a sensor on the machine it's running on, and normalize the data so the correlation is you can understand. Or you have to have something like a syslog server set up where all your different tools log to the syslog server, and the correlation engine takes it from there. But the big point is, before the correlation engine actually gets the data, it should be in a normalized format for two very important reasons. This makes you understand your data much easier, and this makes extending the correlation engine a lot easier. Because the engine I'm going to show, the theory behind the engine I'm going to show today, is a very simple engine, but it can be extended very well. So you want to deal with normalization of data. You want your data in normal format. So you can go to a single point, you can pull out information from your IDS and your vulnerability scanner in a single XML document, for instance. That's always a good thing. Aggregation. You want to see if the aggregation is effective. A lot of people buy security correlation systems, and they'll have a problem where they'll have one aggregation point, which all the security tools send their information to, but they have an overwhelmingly large amount of tools. For instance, 30,000 host sensors, and it's all being reported to one machine. What you basically have at that point is a built-in denial of service attack. You're going to knock your aggregation machine right off the line. And if you can't get the data, the system solution is no good to you. So you've got to make sure that the aggregation point scales well. You've got to make sure that one of the biggest benefits this is going to buy you is reduction of data, which is the entire point of this. You want less data, so it's easier for you to parse, understand, and respond to. You want to make sure that your aggregation point is reducing data as it goes to the correlation engine. Now, the biggest thing, and a lot of people have experienced this, is you have to change your network or the way your business does business to accommodate a security product, and that's not a good thing. A security product should efficiently integrate into your network the way it is. It should complement, not cause changes. Now, of course, if you have a totally insecure network, putting it behind a firewall does change things dramatically. But you don't want to have to do strange things like have to build your own separate network just for the aggregation of data. That's not giving you a good return on investment. You're not spending your time actually fixing problems if you're spending a ton of time just building an infrastructure for what's going to fix your problems. You want to look at your correlation engine. Now, this is a big point. This seems kind of like a no-brainer. It's a no-brainer to me. But you want to make sure your correlation engine works. And by works, I mean, can you reduce the amount of attacks you're seeing against Linux hosts, for instance? Are you cutting the number of false positives you're seeing? Is it being beneficial to you? Are you spending less time going through the drudgery of network forensics and more time actually responding to things? You want to see how extensible it is. A lot of people, I've never been to a company or an organization in my entire life that has all commercially bought apps. A lot of people's applications are grown in-house. And you want to make sure that you can extend whatever you buy or build to include that technology. For instance, if a university were to write their own backup software, but the backup software has a buffer overflow, you want to make sure that the correlation engine can understand that when it sees a packet of this type going to this host, then more likely that's an attack. One of the downfalls of most commercial products are they are not that extensible. In addition to this, you want to see what technology you're using. By technology, I mean how are you coming about your correlation? Are you just doing large data mining sets? Are you just doing stare and compares on different packets to previously stored vulnerability scans? That makes a big difference when you look at the scaling aspect of this correlation engine and how efficient it will be. And I've already mentioned the in-house developed apps. Visualization. This is one of the most key points of a correlation engine or a solution such as this, and people overlook it. Will it be able to effectively show you how to better protect your network? If it can do all, if it's doing the best correlation in the world, but it can't effectively communicate that to the user, it's not doing good. Also, in addition to this, one of the biggest, a big downfall is that you can't look at the raw output of your security tools, meaning that you can't look at the packet contents of your IDS. You just have to trust in the correlation engine telling you that it's a bad thing. Also, one of the things that a lot of people like is a single-click response. For instance, if an infected host inside your network is spewing bad packets everywhere, you can click a button on your GUI and disable the port. That's always nice. Reporting is a very important thing, especially for trending. You can use your trending reports to determine what kind of network attacks you're seeing, how you're seeing it, and how best to solve it. This is good for next year when you're buying new security products. You know what to focus on. Also, what type of reporting mechanisms are supported? Will your correlation tool report to a third party, or will it, or is it a completely in-house solution? Is it a proprietary solution? For instance, can you have your correlation engine send SNMP traps to HP OpenView? Would be a good thing to look at. Does it have a built-in alert capabilities where it can page your system administrator if there's a problem? Can it create a trouble ticket? Things like that. Interoperability is one of the most important parts of this, because if you can't take all the security tools you're using and make them work together, this isn't a very good solution. And very few places buy all their security products from one vendor. Somebody might buy their vulnerability scanner from ISS, their intrusion detection system from Interisys, and Tripwire for host change detection. And with a lot of single vendor solutions, they don't really work that well with things that company doesn't make. So you want to keep this in mind. You want to keep it in mind also when you're designing your correlation engine. One of the biggest aspects, and I mentioned this earlier, is price. These things are expensive. It takes a lot of intelligence to do this, and it's not cheap. There's several approaches you can take to building your own correlation engine. You can do a large technical approach or a small Simple approach. We're going to discuss both of those. The large approach is generally things that will correlate several different technologies: firewalls, IDS, vulnerability scanner, even WTemp logs from Linux machines, and Dr. Watson logs from Windows machines. You want to incorporate as many technologies as possible for the most complete view of your network. You want an advanced correlation engine. You want it to be able to deal with abstract information, meaning that it saw a port scan of this machine 3 weeks ago, and today it saw a telnet session to port 22 from off your site, and tomorrow it saw one packet sent to it. An abstract correlation engine should be able to take all that information and say, I don't know if an attack's going on, but there's definitely worth something looking at there. You need data mining capabilities for what I just mentioned. You need to be able to look at your trends for the last month, last 6 months, last year, because unless you're only concerned about stopping script kiddies or automated attacks, a general attacker will take their time and be methodical about their attack. Meaning it's not going to be quickly. It's not something you're going to see quickly. You're going to take time to recon their target. You're going to take time to prep it, and then the actual compromise. And with the advent of technology like covert channel communications, it's making this kind of correlation harder and harder. It should be able to keep in-depth health information. Now, one of the biggest problems with this type of correlation is the size of data of what you're storing. It's going to get pretty big. Most people want to use something like a SAN for this. But you want to keep in-depth health information. You want to keep the operating system type. You want to keep what ports are open, what services are running. You want to keep a list of who it's talking to, who it has talked to. This helps. One of the biggest things we would do by hand is notice if a machine was compromised. We could take the compromising host, and we could find all the other machines that it talked to, and then take those machines and do an audit on them, and more than likely we found that it's not one single compromise, it's been a string of compromises, which is one of the things you'd want an advanced correlation engine to be able to do. And as I said before, it should be able to detect complex attacks. The smaller approach is what we're going to use. It uses fewer technologies. My engine only uses vulnerability scanning, intrusion detection, and host space changes. I'll discuss that later. But it's a very practical approach. When you're doing this, you want to start off with something small. You don't want to have a goal that's too far outside your reach. You want to make sure it's attainable. You want a very basic engine. You keep very basic host information. Keep this for trending purposes, like what ports are open, and operating system type, both active and passive. You want to do very basic correlation. For instance, Snort sees an alert, and based on the alert, it can reference the host information and tell you if that attack is going to be successful or not. It's useful for only very basic tasks in this realm, but it will cut down on the massive false positives. You want to retain very little information for data mining and trending, because generally the design of a tool like this isn't going to be optimized for large data mines. Although you want to retain enough to understand that a month ago that port 31337 was open on this machine. So you want to keep it's a trade-off between size and space. You want a very specific scope. You do not want to start with a scope that says, I want to build a correlation engine that works with everything and correlates all types of attacks. It never happened. You have to start with a very basic scope. And the scope that I started with was, I want my IDS, my vulnerability detection, my vulnerability scanners to share information and cut down the number of false positives we're seeing. Moving on to reasons why this is good to do, customization of your environment. Nobody really does know your environment better than you. It's hard for a security consultant to come in, take a network diagram and understand the flow, and build a good correlation solution for you in the 2 weeks or month that they're spending on your site. This is mostly because there really are no two networks that are the same. I've done a lot of consulting in my life, and I've never seen two networks set up the same way. So if you start with an in-depth knowledge of your network, you're already a step ahead of people who are building these correlation engines. We briefly discussed it, but the in-house applications and procedures are very important. For instance, your tape backup system, any financial applications your company may have written. There are several companies who write, as we said, several in-house applications. You want your correlation engine to take advantage of these. You want it to watch these because these services are just as vulnerable to anything else being attacked, and you don't want to leave them out in the cold. These systems should augment your infrastructure, not cause you to rebuild it from scratch. We talked about this. I mentioned this once again before briefly. You don't want to have to rebuild your network based on a security tool working correctly. It should augment and work with what you have. Am I boring everybody? No? I'm just wondering. Say again? I'm sorry, I can't do that. If I stand still, I'm like a fish, I'll sink. And that's no good. So you really want to, let me start again. When I approached this problem, I had an in-depth knowledge of the network I was working with. I knew that I couldn't get the network admins to change the way the network was working. And I also knew all the in-house software that was written in policies and procedures, so I had a large advantage over most other people who would do this. And this is one of the best reasons to do it yourself. Before we get started, we talked about your scope. You've got to have clear goals. We're building a small correlation engine. We're only using 5 tools: Nmap, Nessus, Tripwire, Snort, and P0F. Is everybody familiar with P0F? It's a passive fingerprinting tool. You run it on a box in promiscuous mode, and it can give you a semi-accurate guess of what a machine is simply by the type of traffic it sees. This is important because more and more personal firewalls and things of this type are becoming more and more prevalent, meaning that an Nmap scan isn't going to be able to accurately detect what the operating system is, or even attempt at all. For instance, sorry about that. In my group, we are a part of a campus. We're not trusted by anybody, and no part of the campus trusts each other. So most people with personal firewalls and PCs and whatnot block everything that they don't explicitly allow. So I can't even port scan a machine and that may be in another department. This is a problem with correlation because you need to know at least what operating systems it's running. And manually, you can do this really easily by banner checking if it's a web server or things like that. But when you're automating this, it's a bit harder. Your data normalization is something to keep in mind. You got to make sure your data is created in a simple, easy to understand format. All my examples are going to be text strings. They're field separated by the pipe character. Very easy to understand, very easy to process. Now, realistically, when you're building this, you wouldn't. Do you have a question? No. Realistically, when you're building this, you wouldn't want to do that. You want to use a binary format or something to save space and time. You want to make sure that the output generated by your sensors are going to be the same language, basically, which makes it easier to write the correlation engine for. We're going to go with an agent-based approach, which basically means we're going to write some Python scripts, or we have some Python scripts that sit on these hosts that run these tools, and they're going to actually take the information out of the tool, they're going to normalize it and send it to our aggregation point. This cuts down somewhat on some of the technical problems with data normalization. However, it adds a level of complexity that you have agents to maintain. The agents primarily should be gathering information and as much as possible reducing it because you want as little as possible sent to aggregation point, which again will reduce the data. We're going to make a multi-tier system. Everybody's familiar with 3-tier, 2-tier, client server, these types. We want a system that's going to be redundant. The security system won't be any good to us if it's down, if it's broken. It also makes the system more flexible and extensible, and that's one of the big goals we have here is extending our system. Network latency is going to be a big deal, and I actually forgot to put it on the slide, but you should definitely have a network time server. You should have all your machines that are doing this synced, because timing for this is very important. You should want real-time capabilities, meaning that it can alert people in real time when an attack is happening. This means that when you see that hacker doing the SSH attack, it can inform you, and you can actively stop it. This is one of the hardest things to do, but it's necessary for a system like this to succeed. You want a configurable alerting system, meaning that if it's a MSSQL slammer worm hitting a Linux box, you don't ignore it because it's good to know that there's somebody out there, that there's a host out there that's doing this. But you also don't want it to be a critical alert. So you want to be able to build in flexibility of reporting so that when you get an IIS attack against a Windows machine, it's a little bit more critical than a slammer attack against a Windows machine. A slapper attack, I mean. So we're going to go back to our scope, the tools we're going to work with. I wrote this presentation based only on open source tools. We have it running with several closed source tools, such as Lancope and ISS and Interisys. But for this speech only, we're going with closed source, open source, excuse me. And we want to go with the high tech versus low tech. We discussed this briefly. Complex methods of data mining, we're going to avoid that. We want a good attack recognition. The high tech method has a good attack recognition system. The low tech, we just want basically a simple event-driven model. We want a very simple attack recognition system. Basically, what we're trying to do is make sure that alerts seen by Snort will alert us only if it's going to be a successful attack. We don't really care at this point if it fails, because that's good for us. An engine like this won't work with complex attacks, so things like a man-in-the-middle attack or a sequence number-based attack, this won't work with that well, which was a serious problem. We are wholly a data-based tool, which means we can only work with data. We work with data we're given, and we have to collect and store the data. I gotta tell you, I'm really nervous. I'm sorry, I'm sounding like a blabbering idiot. What do we need to accomplish our task? We need host information. This is the biggest part. We need information on all the machines you want protected. Good things to start with, and this isn't a hard and fast rule, but good things to start with are your host name, your IP address, your active and passive OS fingerprints, your date your host was first found, the date your host was first found, the last time that you updated this host record, your open ports, your list of current vulnerabilities. We're going to get into how we do that later. And a list of last IPs that connect to that host, and this is also for data mining light data mining purposes. Security alerts, if any, which means currently that a host is attacking, an outside host is attacking this host. What its threat level is, and that's something that we created to identify the risk that a target has, and a unique host identifier. And we do this to make referencing this host much easier. Now, what I did is this engine is written mostly in C, and it's going to be released open source if anybody wants it. But what I mainly do is this is just a structure. Every time I find a new host, I malloc the memory for it, and it gets pushed onto a singly linked list. And every so often, I have a process that goes through and audits the singly linked list for information it doesn't have, like its host name. It might have a host name but not an IP address. It might have a passive fingerprint but not an active fingerprint. It might not have a list of open ports. And we're going to get into what it does with that information later, but you want continuity of information because this is basically the heart of the system. You need this information to make everything work. We're going to go talk about vulnerability scans. Everybody's going to run Nessus, Retina, ISS, things like that. This is basically how we're doing our correlation. We need up-to-date scans. You need to scan often, and you need to scan deeply. Without these, the correlation is not going to work well. You want to do it often because everybody knows networks change. Time will skew your results. For instance, if you do your Nessus updates on time, and you do a scan today, for instance, of a host, and next week a vulnerability could be released on Monday, and next Thursday, your correlation system will still think, if you haven't updated it, that this host is not vulnerable to anything, which is not good. You want an intrusion detection system. This is key. I use Snort. Most any commercial tool will work, but you basically have to have something that generates in real time. We use a sniffing method, although IPSs, inline prevention systems, are getting more and more popular. But all you basically need is something to generate alerts. Yes? Right.
On the prior slide, you talked about differentiation between active and passive fingerprinting.
Yes.
In what way do you use that information differently? And for that matter, why don't you just rely on truth and sincerity?
Well, being that my network is... Oh, I'm sorry. He was asking why I have both active and passive fingerprinting. And why, since it's my network, don't I rely on what the truth is? And this is a problem with my network. We have 2.5 Class Bs. They're carved up in between different schools and different departments. If we were to try to maintain a central list of that, it would fail, because a lot of the problems are initially DHCP. That would break. Also, you have an admin that decides that this Windows box is broken and he needs to reinstall it and he's going to put Linux on it, and not inform you for 3 weeks. In that 3-week span, that machine is vulnerable to Linux attacks, while your correlation engine only thinks it's vulnerable to Windows attacks. So this is the trust but verify method. You can do that. In fact, we do that. We have a central list, but we don't rely on a central list only. We rely on information we can find, because not everything is always kept up to date. Where was I? Oh, yeah.
Why do you have two fields that bypass the client? Why not just one, say?
Well, he's asking why I have two fields for both active and passive. We're seeing more and more host-based firewalls and whatnot, where a active fingerprint becomes harder to get. But it's better to have a fingerprint of some kind than a fingerprint not at all. Does that make sense? Because the system gathers data from our campus border. So if you go out to the internet, you have to go buy it. So passively, I can pull all the packets I want and analyze it without actively scanning things. Generally, you want both, but generally, you've got to have at least one, because you're dead in the water basically without them. Because the correlation engine works on the principle of it knows what operating systems are and what services it's running, what vulnerabilities it has. Without that, it doesn't work at all. And it's better to have a guess than nothing at all. Did that answer your question? How long should we store data? We store data for a 6-month period. We store all the data we can. Now, there's size constraints there, which are mostly hardware. 6 months of data of this type gets very, very big, especially since we're updating our records every day. So it's depending on your network. For instance, if you're dealing with a company with one class C, that's going to be a lot different than our 2.5 Class Bs, or even a company with a Class A. So it's all depending on your company. And the longer we store data, the more suspect it becomes. As we said, things change over time. So we want to keep up-to-date information, but we don't want to trust older information explicitly, because of the question you just asked, it changes over time. Are we violating any policies? And this was just kind of thrown in as an afterthought. Being that we're a university, we have several acts we have to abide by, the HIPAA Act and things like that. And they deal with how you store information about students, employees, things like that. So storing, for instance, an AIM session from somebody, because one of the tools that I can show you how to integrate is AIM sniff. Storing an AIM conversation from a student over time is kind of illegal. Well, actually, it's an invasion of privacy, and it's illegal under the HIPAA Act. And we can't do that. So you want to make sure that while you're doing this, you're not doing anything that's violating anybody's data retention policies, which the legal department for your company should be able to inform you what that is. Yes?
Typically, you have a acceptable use policy or something that most companies or institutions will say, basically, if you're saying on our network, it's our right to monitor you, and if you don't like it, you don't use the network. Doesn't that give you the right to store those conversations if you log them and process them?
His question was about your general usage policy. Because every company, and I'd be surprised if they don't now, has a general usage policy saying how you can use your network and what the company's rights are in auditing network traffic and your machine, because it's technically company policy. And that gets into a very sticky situation, especially in universities, because technically this is true. Everybody scans their machine. Everybody, when you come to the university, your machine is on our network. We can audit it at will. But policy, implementation of that policy is a little bit differently than the spirit of the policy. We can't go into a dorm room and randomly look through a hard drive for pornography. That's a violation of the personal policy. And at this time, our legal department informs us that although the conversations are traversing our network, that unless it's something that's part of an ongoing investigation, We have no real reason to be reading people's conversations, which is true. So we're invading their privacy when we do it. So we don't. We prefer not to invade privacy, which is kind of strange for a security person to say, but it's true. Also, we're a research institute that does a lot of research. You don't want to make sure you're not storing any sensitive information. I have a funny story about that, where a top secret cleared, a person was sending an email that contained top secret information over a public network, and our sniffer caught it. And following policy when it was informed, and they found out we had a sniffer, they took the hard drives from the sniffer too. So you want to make sure when you do this, you're not storing any information that might be considered sensitive. You want a very clear goal of the information you want to gather. For our engine, we're only gathering host information to either determine whether an attack will succeed or fail. Did that answer your question? All right. Pitfalls, feature creep. I ran into this big time. When you sat down, I'm a coder, which is probably why I'm such a bad speaker. But I'm a coder by nature, and when I sat down, I was like, okay, I only want something that's going to take snort output and compare it to a Nessus database and see if it works, see if the attack's going to fail or succeed. And after a day or so working on this, I'm like, it would be really cool if I could have it scan on demand. So if it gets a snort alert for a machine it doesn't already have, you can go out and scan it and see if it's vulnerable. And this was a big problem for me because before I knew it, this program I was writing was going to cure cancer and control the space shuttle. So you want to avoid that. And it's very easy to do because with the sensibility of the engine, it's tempting to just keep adding little things to it. And that's more of a coding thing than a security thing. But it's one of the big pitfalls I ran into. Adding new functionality. The passive fingerprinting was actually the one thing that got in. I needed it because I couldn't get the accurate port scans of machines, as I said before. So I needed some way to figure out how to do it. It wasn't in the original scope, but it seemed to work out for me. Complexity. You don't want to do things that are too complex. You have a lot of data. You're tempted to start implementing data mining algorithms. Make sure your basic engine works before you, oh my God. Talk about embarrassing. This is not my day. Sorry about that. You don't want to do things that are too complex. These are different models. Say again? No. But I have to say McCaffrey is the best virus scanner I've ever seen. I highly recommend it. There's several different ways you can do this. And this is the next couple of slides, just giving you ideas of ways to do it. We do an agent on a machine, the Nessus machine, the individual machine, that reports to an aggregation point, which attempts to do data reduction before it reports it to a correlation engine, which is actually it's a couple down. But there's all kinds of ways you can do this. You can have an agent report to an aggregation engine, which reports to a machine running correlation engine that actually does SQL queries against another machine. That insulates you against a lot of network failure. If something fails, you can have it fail over to something else. Because, as we said before, we really want to keep this up. That was not all of them. I suppose it was. How did I get there? All right. Well, these are all the different types, and you can read them if you want. The distributed is the distributed is the most reliable, meaning that you can have several different points to do several different jobs. You can have code in your timeout. You can have code in your sensors that if it times out speaking to your first aggregation point, it can talk to the second aggregation point. Then you have timeout code in your aggregation software that if it can't talk to correlation engine A, it talks to correlation engine B, and then your correlation code actually dumps everything in the same database. So it would work. Sir?
What methods are used to ensure that the log data isn't altered at the steps for each process as it's transferred from the device and transported to the various layers?
He's asking how I make sure that my system is not vulnerable to a man-in-the-middle attack. How I'm making sure that my system, the information I'm getting isn't monitored en route to the final destination. SSL. Actually, the next version of this engine is going to have hashing of the alerts and the actions. But as of right now, it's just SSL. This isn't, by the way, this isn't an engine I would take the open source today and try to run on your production network tomorrow. That's not a good idea. This talk is more about how you can build your own than, how mine works. Look, sir?
Did you consider doing out-of-band management so that you will know all of your monitoring hosts and do all of this out-of-band?
I did consider that, but that violates my, you shouldn't have to change your network to make a security solution fit ideology. It would work. We have a lot of things set up like that. And if you have the means, by all means, that's the most secure way to do it. Unless you use VLANs, then that's bad. But that is one approach. But I wanted my information to travel over the public network. I didn't want to have to build an entirely separate network for my solution to work. Do that. All right, we're going to use in my speech, I'm going to talk about the distributed model of architecture. It's flexible, allows most customization. As I told you before, you can have the developer for timeouts and whatnot. It allows for product substitution as you see fit. For instance, if you want to update your aggregation code, it's not a big deal because you have several other aggregation points you can talk to. So as you update it, it won't be a problem. And the same with your correlation engine or your sensors. As long as it's distributed, you don't have to worry about a single point of failure, which is what you want to avoid. It allows for staged development, which is how we did this. Things to consider. Languages. I wrote my engine in C because I like C. C is fast. Java is not. I'm not going to engage in a holy war about Java. I just don't like it. I wrote all my stuff in C. But, write whatever. A version of this is running in our College of Computing. It's written in Perl. So you can really write it anything you want. You want a multi-thread. That's a pretty good idea, considering the task you have. You have, the typical setup for my engine is I have a socket listening thread, a correlation thread, and a DB thread. And they all work together to do the correlation. I can't really imagine doing it that well as a single-threaded model, but it is possible. Make sure whatever language you choose, there's good APIs to the tools you're going to use. For instance, I use the MySQL database as my backend. Make sure whatever language you use, you can talk to whatever tools you want to use to build it. The engine, more so than any other part of the tool, needs to be as fast as possible. You're going to be munging a lot of data, so you want as much speed as you can get. The sensors, the route I went, the sensors are Python scripts. So they're slower and interpreted. But the performance gain we're getting is not going to be on the sensor side, it's going to be on the correlation engine side. You want to, when you're developing this, you want to take into account that this is a system that might be in place for a long time. I'm sure everybody's had that experience where they had to build a solution in 10 days. There's only going to be 2 months and it's going to be replaced with something better. That's how this actually got started. It was going to be replaced by a commercial system. And that was a year or so ago, and we still don't have the commercial system. So in the design phase, although this might just be a stepping stone to a commercial system or something else, you want to make sure that it's not going to, it will stand the test of time. Little problems with this is you hard code IP addresses or whatnot to your code. I mean, this is all basic coding stuff, but these are pitfalls I run into. You hard code IP addresses, you hard code signatures or things like that to your code. That makes maintaining it harder, and one of the things we want to shoot for, and aside from the sensibility, is maintainability. Operating systems. All this stuff works on Linux. My sensors, my aggregation point, my correlation engine, all Linux. That does not mean that other operating systems it won't work on. In fact, porting a Python script to Windows to run a Windows tool or a Windows version of Tripwire is trivial to do. I just haven't done it yet. That's one of the reasons why I want to go with an interpreted language like Python for the sensors. But porting it to other platforms is easier. Storage. We're back to the storage. Data retention. You want to make sure that wherever you're storing this, you have a big enough box, and your database can handle it. The database we use gets very large, which makes SQL queries very slow sometimes, which will in turn make correlating the next event very slow. So as a flow of events come in, you update this host that has this new open port, you update this host with this new vulnerability, you have to make SQL queries for those. Over time, it gets it gets a little bit slower. And you don't want to be waiting on an SQL query for a port update to finish while you have a critical alert pending in a queue. Which brings us to traffic. Traffic's what this is all about. You want to analyze your traffic as well as possible. The biggest thing you want to do, and I keep harping on this because it's the biggest, it's one of the most important steps of this, is data reduction. For instance, on your sensor, you're going to notice that a machine outside that is scanning in will generate, there will be an alarm generated for every host it scans, which isn't that useful to us. That's duplication of data. Although these machines are being scanned, which is it becomes a trade-off. So in my approach, what I've done is I have a host record for the machine that's doing the scanning, the offender, and then it will list the last 10 IP addresses it scanned. And each sensor has a copy of these lists. And as it updates, it can update the list and send it back to the correlation engine. This cuts down on your sensor just sending every alert to the correlation engine because you want to cut down as much as possible. You also want to avoid duplication of data. If you don't want to send an alert to the correlation engine every time a machine port scans a new machine. You don't have to send the entire alert. All you have to do is send the time of the last scan, for instance. You just send differentials, which cuts down on data. You also don't want to be sending large amounts of data to your aggregation correlation engines. You might inadvertently cause a non-service attack. Bottlenecks. And this is an interesting problem we had to overcome. The aggregation point has to be beefy enough to handle all the sensors that's communicating with it, which is kind of hard if you have thousands of sensors. So you got to make sure you have enough aggregation points so that when your data is being communicated to it, it's available. You got to make sure your engine can keep up with the amount of data it has to process. You got to make sure your database isn't going to die. And interoperability. We have an existing network management solution in place, and I don't want to replace that with my tool. I just want to make it aware of me by sending SMP traps and whatnot. Other correlation tools, this may be a stepping stone for many people into a commercial product. And if that is the case, then you want your tool to work with other tools. Some tools take XML input as alerts, and that's pretty easy to do. Also, in a lot of places, well, universities mostly, it's not as prevalent in industry, you have several different groups that do the same job. Like, for instance, at Georgia Tech, we have the College of Computing, we have the College of Engineering, and we have the Industrial Science Department, who have all their own IT staff. And they want to take care of all their stuff internal. They don't want anyone else to touch it. So if this is the case in an organization you're in, you want to make sure that your correlation engine can inform them of stuff that's going on. And likewise, if they have a correlation engine, it informs you. Sure. Say again, sir?
Have you considered the integration of your tool with the Purdue detection system or something like that?
Yes. My tool is designed to integrate into anything. If you want to integrate my tool into your 57 Chevy, it will work. It's designed to be as extensible as possible. Actually, the speaker that's coming right after me, I can't remember his name, he's speaking on Spider, is one of the things I'm interested in integrating with. But it's designed to integrate with other things. And I have thought about it. It's just we haven't had the time to do it yet. He was asking if I thought about integrating my tool with others. Communication. We're going to get data from point A to point B. He asked a question earlier. How do I keep it secure? We do everything over SSL tunneling with certificate authentication. That gives you some measure of security. If you're a determined attacker, it's trivially defeatable, but it will keep the script kiddies out, which is what I was going for. Believe it or not, on my college campus, we have lots of script kiddies. We have a thick agent, which means an agent does as much processing as possible before it sends the data to an aggregation point, which means when the agent first loads up, it requests a list of host info for the ranges it's protecting from the correlation engine. So it's going to basically get a list of all the machines that it's watching. And anything that can be reduced on the agent side will be, which is helping our correlation engine as a whole. The normalization, This was originally designed to work with XML, which is, as everybody knows, a great industry standard. And there's many open source parsers that exist for this if you don't want to write your own. I eventually went with a custom communication scheme, simply because I wanted to, I wanted more granular control over it, which I'm not saying that XML doesn't give me, it's just that I wanted to write my own. This is how the agent actually does data reduction. The agent will boot up. It has a config file. It grabs a config file and it looks for the type of agent it is, which is either an intrusion agent or a scanning agent. It will then determine, based on its role, pull a list of information from the correlation engine. And that information is the host information for the host it's protecting. It has a local copy it tries to pull from first, but if the copy is too old, it will go to correlation engine. Or if the hash on the information has been changed, it will go to correlation engine. Informational alerts, which are like, this host now has port 80 open, will only be sent if it's new. If it won't, as it does a port scan of something, it won't send ports to the correlation engine that already exist or that it already knows about. It will only send new things, which helps out a lot. Simply because the less time you spend on the trivial things, the more time you can spend doing the important stuff. The changes in attack information. When the intrusion sensor detects an attack, that's sent immediately. We want that sent as quickly as possible. The engine config tells the engine the address ranges of everything that is being configured, being protected, meaning that this is where I have all of our IP addresses we're worried about in it. A network baseline has to be created first to start with. This is a vulnerability scan of everything you're protecting. Without that, it's kind of hard to detect changes because everything's a change, which was the original way it was designed. I decided not to go with that because as new things happened, it would actually bog the system down. So you want to start off with a good baseline. The information differences are received by the engine, applied to host information in memory, and written to the database as soon as possible. I do as much as possible in memory. It's a lot faster than querying the engine. Now, if you're running multiple correlation engines, you've got to write to the database as quickly as possible because your other engine might need that information you have only in memory. It's a trade-off, and that's up to the individual coder. I designed my own communication protocol for that, and it's a really simple protocol. Please don't laugh. But it's just a simple text string field separated by pipes. And as you can see, it has, actually these aren't capitalized. In the actual protocol, the actual boldface are all lowercase. Basically what it is I have one of these things, action colon, and a value. Pipe, time colon, and a value. Pipe. This is for making parsing easier. You can build your string in any real form. You can go through and string toke it, and it makes parsing somewhat easier. Basically, what we start off with is an action. 0 is informational, and an informational alert is the type of alert it is. We have a new port open. We have a new host we found. This host changed operating system type. This is anything that's not an intrusion, basically. 1 is an alert. An alert is an intrusion. So basically, when we designed our parsing structure, we said if 1, we parse first. If not, we worry about it later. Now, this engine has the ability, and we're going to get into this a little bit later, to request sensors do stuff for it. Like if it gets an alert for a machine it doesn't have any host information for, it will go find the host information. It won't be as accurate at this time because this is after a probable attack has happened, but once again, it's better than nothing. So when the engine is requesting something, that field set to a 2, and a 3 is a request from that response. And the request from the response is processed just like anything else that comes in. Time is epic time, since 70. As I mentioned before, everything on the network is NTP'd, so we can keep a pretty good accounting of what's happening at what time. With the time skew, some things might not work quite right. Sensor ID. I require an NTP client. Well, we require an NTP client to be installed on everything, which is why in my client there is no NTP client. On the next version, there is an NTP client that is built in. But at this time, because this was originally built to work on our network, we didn't need it because everything worked on NTP anyway. And if it didn't, we would require it when we're installing the sensor. Now, sensor ID has several roles, whether it's originating or the destination of the alert. But basically, it's just an int that's a unique identifier for that sensor. The source is as I said, it's the source of the action, whatever it may be. Des is destination of the action. Port. These are different things that can happen. Port change, vuln ID, the attack. SID is the snort ID of the attack, as we use the snort ID a lot. The threat level is a unique value we came up with based on how many machines are talking to it, how many security alerts we've seen, whether it be low or high. Basically what the current is, so we can go into a host table and query with something like select star from host info where threat level is greater than 50. We limit our host level at 100. Request ID is the type of request. This is implemented by the engine when it's sending out a request to a sensor. A 0 is a port scan, 1 is IDS logging, and 2 checks for intrusion, which means that if a machine's running a host sensor on it, and actually I'll get to that in a second. I don't want to get ahead of myself. This is basically a breakdown on how this protocol works. There's a request validation function when it first gets a request. Make sure it's a valid request. If it's not, it's dropped. But there's several things that have to happen for it to be a valid request. A string must contain at least action time and sensor. It's got to contain at least those 3 fields, if nothing more. Whenever an informational alert is created, the source is set to the machine that had the change. If no type change is sent, it is not a valid request. Which means if the action is an informational update, but there is no port change or whatnot, it doesn't update it. It's an invalid request. When an alert is generated, source is set to the attacker, destination is sent to the victim. So if you have an attack alert and we don't have one of these 2 fields in it, it's an invalid alert. Even if we don't put the type of attack. If action is set to alert, there is no attack, and it's an invalid request. When an engine makes a request to a sensor, set to the ID of the sensor, and the request is what's destined to. The source is sent to the IP to execute the request on. Basically what this means is when the engine decides that it needs some information it doesn't have, like the process I mentioned that goes through an audits to make sure it has a path of an active fingerprint, last change time and whatnot. Basically when the engine makes a request, it sets the ID of the sensor it wants to execute the request, and the source is set to the request to the sensor that set to the IP address that's going to be executed on. And then, of course, there's a sensor field. These are examples of it. They kind of got wrapped because of size constraints. But this is what the first one is what an updating a host profile looks like, basically. We've got action 0, time is the time in epic, the sensor ID, the source, and what's changed. That's the plus 80/T is telling me that I now have an open TCP port, which, as you can see, if anybody's ever written C, this is a pretty easy string to parse from a C standpoint. And it's got 4 more examples: the sensor alerting the engine to an attack, the engine requesting the port scan of a host, and the engine the result of the request. Does anybody have any questions about this? All right. Sensors. Say again. I want to write my own. There's no good reason not to. I just want to write my own. The next version is wholly XML, but the original version was a custom string for parsing. What sensors? We're using IDS, vulnerability, passive, and host change detection. Basically, I'm going to do the flow? No, not yet. Basically, the way this works is, imagine, if you will, a network. Let's go with the latest exploit, a DCOM exploit. A DCOM exploit is sent to a Linux machine. Snort sees it, there's a rule for it, it flags it. The sensor has the host information for that host. It says decom exploit is a Windows exploit. This is a Linux machine. Will not work. Let's send an informational alert saying, telling it to increment its threat level. But that's about it. The resulting, the flip side of that is you have a old Linux machine running an older version of SSH. Somebody does a CRC32 exploit against it. The snort sensor picks it up. The sensor says, well, this is a CRC32 exploit. This machine is running SSH. Let's generate an alert and send it to correlation engine. The correlation engine will receive it. It will look at the Nessus IDs that are currently vulnerable in that box. It will determine that this snort ID is vulnerable, has a high success rate against this Nessus ID. It will increment the threat level and alert someone. That's basically how the flow works. So, actually, the next couple slides are kind of dumb. They're just stuff about the effective placement of the IDS. You know, you have to have it in promiscuous mode for it to work well. You should try to limit the amount of address ranges per sensor to cut down on noise. Your vulnerability scanner, we have a unique setup with a vulnerability scanner as we don't have a firewall at our border, but we have access control lists to block things like port 135 and 139. And one of the things we use this for is accidental deletions of those access control lists. It's happened a couple of times. So we have a unique view of the host inside where we can see all of these ports. Several of these ports are being blocked by the router. We have an outside host that's also scanning it. And if the outside host and the inside host have basically the same view, then something's happened. And we can tell that something's wrong with the router, which is one great use of this. I generally use Nmap just for port scanning because Nessus is a bit overkill. Everybody who's ever run a vulnerability scanner knows just to get the port information on the host, a vulnerability scanner is a bit of an overkill, which is why I'm using Nmap and Nessus instead of just Nessus. Although you can make you can craft your request to have your Nessus engine do your Nmap request and report it back, but it was just simpler to have a Python script exec Nmap and report the results. Network speed, network size, number of attacks. This is all gauging information on your network. How big is your network? What do you want to protect? How fast is your network? Do you have something that can sniff it? A lot of problems with a correlation engine are IDSs that drop packets. We found this out, that if you are not getting you're not getting accurate network information, your correlation engine is pretty useless. Meaning that if you're missing every third packet, you might be missing an attack, and your correlation engine is not going to be able to help you with that. So when you design the placement of your sensors and whatnot, you make sure that you're not dropping packets. The number of attacks. So our correlation engine deals with a large number of attacks. This is because everybody likes Georgia Tech, I suppose. We try to prioritize attacks based on, as I've said several times, based on its success, if it could work. Yes? That's what we do. Now,
You scan all 65,000 ports on 2 Class Bs every 24 hours?
have you ever heard of ScanRand by Dan Kaminsky? No. Dan Kaminsky gave a great speech yesterday, and ScanRand is a high-speed port scanner that enables that. Whereas scanning for one port in a 2.5 Class Bs takes 2 hours with Nmap. With ScanRand, we can scan the entire campus, all 65,535 TCP ports, in a little over an hour. Well, we do UDP. That was just my TCP example. We do that. Now, based on what your correlation engine is protecting, which is part of your gauging method, we might not decide to protect all 2.5 Class Bs. We have half of a Class B dedicated to ResNet, which are students. We might decide that that's the Wild West. We just don't want to protect that. So we would configure a correlation engine not to worry about those hosts. Only scan critical hosts that we worry about. But I try to make sure my host records don't get older than 24 hours. Because, like I said, lots of things change. If somebody comes in today and decides that they want to run a new service on their box that's bad, you want to know about it generally before an attacker does. And 24-hour periods is generally, at least encompass some part of one workday, unless it's the weekend. But I feel strongly that you need to keep up-to-date information on this. His question, I should repeat it first, was we have 2.5 Class Bs, which is a lot of hosts, and he was asking if I scan all of those every 24 hours. And yes, we do. Which was my scan run example. Active sensors versus passive sensors. Active sensors are sensors that can not only receive, they can not only generate requests, but receive requests from the correlation engine and update them. An example of this request would be an Nmap sensor. Nmap sensors generate information based on their general normal scanning patterns. Also, when needs be, the correlation engine can request that the Nmap sensor do a scan of a particular host and report the results. This is an active sensor. Active sensors can encompass many different things on several hosts. This can go up to including firewall rules, where we have several hosts where if there's a problem, we can, when there's an attacking host found, we can, you go through the correlation engine, and the correlation engine will request that the host be blocked via IP tables, or drop in a host.deny at least. So it's basically anything that can generate, you can generate and receive requests from the correlation, generate requests for and receive requests from the correlation engine. Passive are sensors that only generate information that goes to it. P0F is an example of a passive sensor, as it doesn't do anything other than remotely sniff and send information to the correlation engine. The engine, what it does, our engine is only going to verify the attacks being, if an attack being seen may succeed. It maintains the host information for all the agents and makes necessary alerts to responsible parties. Engine's kept very simple. The correlation engine is a little less than 5,000 lines of C, so it's a pretty simple engine. Unnecessary functions. Somebody asked about integrating an NTP client into it. That's best left being handled by something else, although the agents will have that feature. We talked about feature creep and the harder program, the main resolve loop, because there's a main loop that all the threads basically go through. And this is the logic that the correlation engine uses. If an IDS alarm is created and it's sent to the engine as soon as possible. Any other question? No. Based on stored host information, as you can determine if the attack is likely to succeed and change the host threat level. Host threat level is what we care about because that's what we see as users of the system. A thread will audit a queue for machines with threat level greater than a set value. When we have a threshold, our threat level goes up to 100, we have a threshold of 50. Just informational alerts can't get the threat level higher than 50. But if your threat level is higher than 50, something strange is going on. It can inform the admin. If a host has an active sensor, the engine can request that the host check itself to see if it's been compromised. Meaning that if tripwire is on this host, and in its host table it sees that it has it, it can generate a request to run tripwire and report the results, seeing if anything's been modified, or if there's any new files on the file system, things like that. Which kind of is a strange problem because every time you run tripwire, it finds like temp files and things like that. We had to deal with parsing those out, which is actually a problem with this system because if you hide most of what you're doing in a temp file, in a temp directory, we're going to kind of miss it on the host checks, but that's all fixed in the next version. Data, the host information, I said this before, for simple ease of use, for ease of example of what I'm showing, is a simple linked list. Contains all the information we have on a host. Everything, I like linked lists for simplicity because even freshman CS students understand what a linked list is. So when I'm explaining it to somebody, I don't have to go into great detail about how a linked list works. So everything basically is a linked list. My alert queue is a linked list. My alert queue is a queue that holds all the machines that are currently waiting to be processed for alert. The information queue, active queue, request queue, and sensor queue. They all have their descriptions of what they do. But basically, we have a whole bunch of singly linked lists that we traverse for information. This is how it works step by step. If there's anything in the alert queue waiting, if so, we process them immediately. Are there any actions waiting to be processed, which is informational updates, things like that. We process. We read them off the socket, and we put them in the appropriate queue. We determine if an action is an informational or an alert, because we basically just read this off the socket. So we determine if it's an informational action or if it's an alert. If it's an alert, we put it in the alert queue right away. If it's an action, we put it in the action queue. Once again, we go back and we check the alert queue, see if we have anything new that we just put in there. If so, we process it. Then we check the information queue, process as permitting. This is where the prioritizing of information came in. We will much rather process alerts than information, although there's a sliding window for processing information. This is basically the alert process step by step. By the way, you guys don't have this PowerPoint presentation because it was updated yesterday, but it will be available on the Black Hat site shortly. This is how the alert processing happens. Determine what host is being attacked and what the attack is by parsing the string. Check the active alert queue to see if there's an ongoing attack, meaning if this is a second alert received for the same host. Check the host information for the victim, determine if an attack may or may not succeed based on CVE information. This is outdated. I don't use CVE anymore. I have a language I wrote to do this, which isn't better than CVE. It just works better for this tool. If the attack has a good chance to succeed, give the host a critical threat level. If it has a low likelihood of success, give a low threat level warning so the admins will know something's going on, but it's not critical. Check the host information to see if there's an active host sensor on it. If so, send a request to do a self-check until otherwise informed. If a response is received, and then if a response is received that the host has been compromised, take steps to lock the machine down. This is what we're talking about, the host.deny and the IP tables. If you have a checkpoint or IP table-based firewall, you can lock it down. Check to see if any alerts have been acknowledged. If so, remove them from the alert queue, eliminating the false positives. This is the same example I've been using most of the day, the MSSQL Slammer one. So we can play that. This is how it works. During the height of the Slammer worm, we were receiving several million alerts per minute, which was actually bad. And this correlation engine helped cut a lot of those down. So we were able to find just unique hosts that were infected with Slammer instead of every alert generated by the host. VNL is the language I just mentioned, vulnerability normalization language. What is it? It's a way of comparing unlike things. It sounds kind of strange, but basically it allows you to take two different things like a snort ID and a Nessus ID and determine if they're going to work well, if the attack's going to succeed. It's used on both the engine and the sensor, mostly in the engine. It's a simple language like the communication protocol. Simple, easy to read. This is what the VNL protocol looks like. And down at the bottom is an example of it. Is there any questions on that? Yes. Yes. Next version. This was my lots of mistakes version. Everybody has those. Have you ever used ISS 1.0? Lots of mistakes. But 7.0 is pretty good. Not that it's a vendor pitch or anything, just an example. Concerns, bottlenecks, too much information created on a large network, that's a possibility. Man, I'm not going to get a spot like that. That's nice. Extendability. Engines should be designed to evolve. We've talked about this, essential goals. We've talked about all this. I got ahead of myself actually on my slides by explaining some things. Problems. You are only as good as your tools, meaning that if your Nessus plugins are out of date, you are out of date. You no longer have a good functioning correlation system. You can miss things. Your IDS rules are the same way. Maintenance, things that will break. Communication between the hosts. You need to make sure you need to make sure that that's not a problem. Things that will break, misconfigurations. We originally had some bad code to determine every host that had a port open as a critical vulnerable host. So you want to watch out for those pitfalls. There are many things in the future that this will work with. Almost any open source tool you can integrate into this. Commercial tools, if anybody runs a Langcope or a ISS or an Interisys IDS, we have Python code that will extract information from them and run it. Making the engine more complex, more data mining. The next time I give this talk, it's going to be a much better talk, but it will go from the the very simple, basic engine to a more advanced correlation engine. Dark security. Is anybody familiar with this term? Dark security is where you protect people you don't know they don't know you're protecting, which was actually originated by a guy named Thad Starner, who does a lot of ubiquitous computing stuff. It came out of an experiment where people on a Navy ship wore badges that would talk to an RFID when they walked through a door, so they could plot the path of a person walking. So basically, a captain of a ship could tell where people were at any time. But people really don't know that's how it works. So it's something similar. One of the things the correlation engine does is everybody has security badges. They allow you to badge in and out of buildings, check in the morning and whatnot. One of the things that my correlation engine, the current version we run, does is check to see if you're in the office. If you're in the office and your machine, if you're not in the office and your machine is doing a lot of traffic, that's kind of strange. Now, if you've connected to your machine from home and you're doing a lot of traffic, that's one thing. But if it's looking for things that are compromised while you're not there. If it's 3 a.m. and your machine's doing 40 megabits of traffic, there's generally something wrong with that. That's one of the examples of the more abstract things that can be added to the correlation engine. More types of sensors, and we talked about this, basically any kind of open source tool. And that was it. Yep, any questions? Comments, suggestions? Should I stop speaking publicly? I think I should. Yes?
So how do you actually do the mapping between the vulnerabilities and the IIS
No.
attacks? Do you do that by hand?
That was a part, and as soon as you mentioned it, I realized I left that entire thing out of the speech. There's basically the VNL, where you write rules that say, this snort ID can be penetrated by this machine. So your engine basically checks the VNL for what's vulnerable and what's not. So when it gets a snort ID with a SID, it checks it against the VNL rules to see if that SID is vulnerable by anything on that's currently running on that machine. Yes. That's the manual process. But after that, it's all automated. You generate those by hand. Was that what you were asking? Oh, okay. Yeah, those you actually write those much like you would write a snort rule. That basically says this SID can't penetrate a machine with this Nessus ID. So that lets you put only attacks you're really interested in putting in place. For instance, both have a lot of really esoteric attacks that you probably never see, like attacks against Alcatel phones. We've never actually seen that, so we pruned that rule out. So we only have things we're interested in our VNL. Yes, sir? Yeah, that was the other part I left out. I'm really sorry. This is the first time I've done public speaking like this. But what it is a PHP front end to the database, and it's really simple to write. I picked PHP because PHP is really simple to write and extend. Sir. Yes, sir.
So the triggers your alerting system is the IDS alerts. However, you can probably trigger that from other systems, right? Like vulnerable scanner. So for example, you have a vulnerability on your system. It could be that IDS has data already or whatever. So can you take also those as triggers for your alerting pieces?
Now, the engine I'm describing here was the absolute first engine we wrote, which is being released open source. The current engine, if a vulnerability scan detects a host that is currently vulnerable to something, it will send an alert to an intrusion sensor to up the watchability of that host is what we call it. We call it the watch level. So it keeps logging for that host a little bit longer than it does other hosts. So basically, what we want is it triggering off both the intrusion and the vulnerability side.
Right, but you're assuming that your IDS will catch them, right? And that's a piece that I would say I'm not so comfortable with that.
Well, right. Well, this is the 80-20 solution. We're trying to get as much as possible in the first version. The next version, there's different kinds of intrusion sensors, which will help mitigate some of those doubts, because I also doubt that Snort's going to catch every attack, but it's a better start than nothing. Yes?
I understand your reasoning for building your own. I'm trying to evaluate what's worthwhile for everybody to build their own. You mentioned at the beginning that you guys were seeing about 10 million events per day. If you implemented this type of correlation, I'm curious what kind of reduction did you see once you implemented this, and how long did it take you to design and build it?
It took a month or so to go from idea to production. We saw a reduction down to about 3,000 alerts a day from around 10 million, which made it much more manageable on our part.
How many people did it take a month to write C code in Python?
Oh, that was just me. It took about a month. But there are 24 hours a day. This was mostly done not for Georgia Tech, but because I just wanted to write a tool that would do this, that could be released open source. Yeah. Well, I don't have much of a life. I just code. I'm sure a lot of people share that sentiment. So it wasn't really that much of a change. It was a month of evenings and weekends. And the biggest part was the testing to make sure that everything scaled well. Because I would design it initially on my network at home, and then I would go in and install a couple of sensors, and I would go from generating like 15 to 20 alerts a minute to generating 15 to 20,000 alerts a minute, and that would kill the code. So it had to be. I had a learning period of making sure it scaled well. We haven't seen a top end. Is anybody familiar with the spike fuzzer by David Tell? We fuzz it a lot, and it hasn't crashed yet. So I don't have a theoretical maximum. It's based on the hardware you're running it on, and there's so many smaller parts that would make up your maximum number of alerts you can handle per minute or per day or whatnot.
Is your engine purely multi-threaded?
Yes, it's POSIX threaded, which is what my engine is designed to run on a Linux machine. I'm working on the Python and whatnot for Windows machines. I don't think I'm going to port the engine to Windows, but it works well on Linux. Yes?
What database are you using? How large a scale is 6 months worth of data?
Well, we had to implement some data reduction. 6 months ago, we can't see everything we can see on the same host today. We can see, 6 months ago, we could see the host and the information, like the operating system type and whatnot. We don't keep the vulnerability information after a month or the open port information, but we keep that it was found. We use MySQL, and it scales pretty well. Although it's designed where you can remove MySQL and drop in any database you want, as long as it's a SQL-compliant database. And I didn't tell you guys where to get the tool. It'll be on the Black Hat side as well. Should have a checklist of things I forgot. Any other questions, comments, suggestions? Yes?
I'm sorry, you mentioned you were testing the upper limit, I didn't hear the tool.
Spike. Well, that's not so much for testing the tool as testing the load and the quality of the code itself. Are you familiar with the spike fuzzer? Well, there's a guy running around here named David Tell, and if you stop him and ask him about it, he'll tell you all about it. But basically, it's a testing methodology where you generate everything that could possibly be seen and throw it at the engine and see what happens. So we haven't had it crash under heavy load, but I can accurately gauge what it scales to based on hardware requirements and whatnot. Any other questions? Oh, yes.
You mentioned that you keep data for 6 months.
Yep.
What volume of data or how much data do you gather in a 6 month period on a detail like that?
About 900 gigabytes. We have it in it's being stored on a Sunbox V880 with a bunch of 73 gig disks. Yes. Well, right now, we don't handle it very well. We're going to replace the MySQL database with an Oracle database, and rewrite a lot of the simple C that the MySQL API with PLSQL stuff to make it faster. can do in a period of time. We can do close to 700 per second. And that's running on a dual processor 2.4 gigahertz machine, running the 241820 kernel right now with a, that's on a 2.4 gigahertz Linux machine with a 2418 Linux kernel with a Ultra 160 drive or drives. That's a MySQL database. Now, what we do is, after an amount of time, we will replicate that database to a machine with much more space, which is the Sun V880. We don't insert directly into the V880. We have a mediator. Any other questions? Thank you for coming. Please, really, as I mentioned, this is my first speech, so if some of you want to stay around and tell me what I did wrong, I'd be more than happy to talk to you. Thanks a lot.